All right, good morning and welcome, or welcome back, I guess, if you joined us during any of the two previous days. This is Metal Forming Magazine and PMA's fifth annual Internet of Things experience for manufacturers. And unfortunately, this time we had to present it as a series of webinars. Hopefully we'll be live and in person again next year. My name is Brad Kuvan. I'm the editorial director at Metal Forming Magazine and PMA, and I'm pleased to serve as your moderator. As mentioned during previous sessions, this meeting and all the others in our series is being recorded for archiving. And the recorded event, along with the presentations, will be posted to our website probably early next week. So we'll let you know via email when the webinars and the presentations are available for viewing online. All participants in the meeting are in listen-only mode, which means that the speaker and other listeners can't hear any audio from your site during the program. However, if you need to communicate with us, you can submit any questions and comments using the question box located on the control panel of your go-to screen. Simply type your question and use the pull-down menu to select Organizer to post your question to us or your comment. Then you'll use that same question panel to pose questions to our speakers at the end of each presentation. Lastly, before we get started, I want to thank our event sponsors, Komatsu and Munis. Without their support, we would not be able to do events like this one to you, so much thanks to Komatsu and Munis. So we'll go ahead and begin this morning's webinar session. And we begin with a talk on how Industry 4.0 will help manufacturers overcome perpetual workforce shortages. Our speaker is Chuck Werner. Chuck is the Manager of Operational Excellence at the Michigan Manufacturing Technology Center. There's Chuck. He's worked there since 2016 with his areas of expertise are in Lean, Six Sigma, Industry 4.0, and quality. Recently, the Michigan Economic Development Corp has partnered with the Michigan Manufacturing Technology Center and Automation Alley to create the Real Factory 4.0. So Chuck's presentation is going to discuss how Real Factory 4.0 is helping small to medium-sized Michigan manufacturing companies realize the benefits of smart manufacturing and overcome perpetual workforce shortages. Before Chuck starts, I just want to let everybody know that there are a couple of videos in his presentation. The sound for those videos won't play over your phone, so if you're using your phone to listen in, you'll have to switch your audio over to the computer to hear the sound. So when you do that, just make sure your volume is turned up. I don't know, Chuck, if the sound is not critical on the videos, but sometimes we get feedback from our attendees that they can't hear the audio from the videos. So anyway, with that, we'll go ahead and welcome Chuck.
Morning, everybody. We're going to start out and talk about Manufacturing Technologies Industry 4.0. Kind of already introduced. I'm Chuck Werner. I'm part of the team out here at the Michigan MEP, also known as the Center. I've been here for a while, and actually with regards to Technology and Industry 4.0, we've been involved in our activities for about 3.5, going on 4 years now. We are an MEP, which means we're a 501c and a nonprofit. We are the Michigan MEP, but there's one in every state and Puerto Rico, and we have various regional offices so that we can get anywhere within the state. Lots of ways to get in touch with us. You can see we have the center.org, always a good way to contact. We are on LinkedIn, Facebook, and the blog, and I believe we have some sort of Twitter presence, but I'm not a Twitterer. Everybody kind of knows about industrial revolutions and Industry 4.0. What it is, it's just a series of disruptive technologies that kind of change the way we do business. And one of the things that we're looking at is how do we apply it in our own business? And there's two ways to kind of look at it. And I put this up because there's a lot of people out there that will typically tell a business, if you don't have all these technologies in 3 years or in some time frame, you're extinct. We don't necessarily follow that methodology. Instead, we favor what we call the adoption roadmap. And that's basically beginning with an understanding of what's going to help your business. There's no use in, I think of, 3D printers are going out. I've seen robots on floors where we've brought technology in, but there's not really a plan or a tie to our business need. and these things go unrecognized, unused, or even worse, a technology that doesn't really drive to the bottom line becomes kind of a good reason not to do it again, or maybe a good reason not to invest in the business. So we like to understand the voice of business and the voice of customer. We like to educate people, and we'll show a couple of ways that we do that. And then we want a company or a business to build a vision and go forward. Start small, prove something out, see an ROI, and then kind of build on the wins behind that. We are part of a partnership with the MEDC and Automation Alley. Started last year. Our goal is to get to 6,200 minimum businesses and be able to perform an Industry 4.0 technology assessment, bringing awareness, but then also giving an opportunity to engage with and help assist in these technology implementations to make sure that they are successful. I'm showing our assessment. The main point that I really want people to understand is have a plan, have an assessment, have some kind of an idea of what your business wants, what it's calling out for. This is the one that we use. It's about 40 questions and takes 2 hours. I'm gonna, in full disclosure, probably another hour of your time to do a review, and then if there's activities going forward, we can work that out as we go. But the important thing is to be able to kind of look at it and analyze, what's our strategy, what's our business strategy and our needs. What do we currently have as far as interconnectivity and an infrastructure? So what sort of investment are we looking at to kind of drive a cost discussion? What information systems do we currently have to run our business? And then how do we run our day-to-day operations? It allows people to tie to, again, their specific needs. We're looking for that one-to-one correlation between an investment or an implementation and a problem that it's going to solve. We do also do a roadshow, so I'll show you a little bit of our environment here in a bit. But one of the things that we like to do from the education as we're headed down that roadmap standpoint is actually go on site. And this is actually a picture of us setting up the roadshow at the Kalamazoo Air Museum. But being able to bring about, I'm going to say 85% right now of our technology loaded in a trailer and set it up and actually let people get hands-on, because part of the education is not to try and make things look, super high level, but to make sure that people understand how simple some of these implementations really are. And you can see here some shots of the lab, various technologies. We actually have all 9 of the Industry 4.0 technologies that we can show people, and we'll get into some of the ones that'll help specifically to how we address worker shortage. This is the lab actually where I'm sitting right now, where we hold our classes as well as get hands up. And a couple of things that I want to touch on. So here's just a headline from CNN Business, and it's from 25 October of 21, and basically talking about how 47% of their respondents in a survey were reporting that they can't find enough employees. And I know that that's a problem that I see virtually in every company I've done. About 150 assessments last year, with more to follow this year, and we're seeing the same thing. And I want everybody to realize, because one of the things that we keep telling ourselves is it's going to get better, it's going to get better, it's going to get better, it's going to get better. Here's one from America's Credit Union 2019. 98.6% of American manufacturers are small businesses struggling to hire, and I will tell you firsthand, as a plant and operations manager 6 years ago, we were seeing the same trend back then. So in some cases, it may not get better as far as the ease of finding employees and or retaining them in our workplaces. So just kind of an example, right, of a business and a small operation, and we can see the various departments, and if yours looks like this, thank you very much, congratulations. Send me a line, because I would love to come figure out how you're doing it. Typically though, we're not staffed quite that perfectly. You see the red here, these are jobs that we're trying to fill. or some open positions that we have. And a lot of times to deal with those, particularly when we're talking in a small businesses, we'll start to look at the cross functionality or the cross training of our people, and we may shift associates. So in this case, we have a materials operator that also knows how to run a machine. So hey, can we pull them off of a high-low and have them run? And sometimes we do that a lot. We start pulling right from the area. Well, that puts an extra workload. We saw the same thing during the automotive downturn, but specifically in the materials maintenance, we start pulling people around. Jobs get harder, tasks get a little bit more, and that ends up in, right, we don't find the replacement, we don't keep the people, we actually start losing people because we start leaning on them too heavily. I've seen that a lot, particularly in the maintenance world and engineering. So I want to take a second and kind of look at a couple of things that we can do in our small to medium businesses to approach from another thought process. And this one may not be popular, but one of our favorite quotes is, "There's nothing quite so useless as doing with great efficiency something that should not be done at all." I know there's a big push. We got to get out there. We can't find workers. We need to automate. And I certainly am a fan of using automation and robotics. But the concern is sometimes we'll go out there and we'll want to implement. I had a client that once said, can you automate the cutting out of a defect? I said, cool, what defect are we cutting out? They said, we don't know, we can't really see it, but the system tells us it's there. Don't automate waste, right? So think about lean, our waste, our product time, our cost. Anything that doesn't add value for the customer is waste. Going and getting information. And on this next slide, you can kind of see the overall waste wheel, or the 8 forms of waste. Make sure that you're trying to eliminate that waste first. And this isn't just at the shop floor level. A lot of times we look at just our processes, but when we're looking at being able to run our business, we have to consider such things as how long or how much time do we spend in gathering data or in finding where a problem is and being able to respond to it. And how do we find that waste? How do we know where it is in our business? This is another lesson learned from many of the assessments that we've performed. That begins by understanding how we run our business. And this is just a quick model, right? Obviously, we have a product or a process, we have a business plan, we get the resources that we need in order to run it, we get the scheduling of what order we want to produce, we cut them loose. And unfortunately, in a lot of the businesses that we interact with, this is kind of where the loop goes. I run at the end of the month, I get in my accounting system, I take a look at whether or not I was profitable up in the business planning and strategic area. And if I made money or I lost money, I try to figure out how to either do it or not do it in the next month, depending on how that applies. What we're trying to do is we're trying to get people to think a little bit differently. What we want to do is make sure that we're actually collecting that information from the shop floor. And again, I was a black belt back in '96. So as I like to think of it, Six Sigma before it was cool. But on the data collection end of things, back in the day, we used to hand everybody sheets, make them fill it out, have supervisors make sure the process was being done, make sure they all got put into a program that we could then take into an analytics that we could then put into PowerPoint. A lot of companies don't have that kind of people. So we start talking about being able to analyze. But if we get that data, we can start watching it over time. And as we watch it over time, we can start analyzing the data. And obviously then if we analyze our data, that opens up a whole new world for how we're going to manage our business at the senior level, right? We're going to be able to see that operational performance. We can start measuring measurements. We can start getting an expectation for how the business is supposed to run. And we're going to be able to tie that, and this is really the key important thing that we're looking at. We can tie our performance to our cost, so that we can actually, through a waterfall or other analysis, figure out what our biggest problems are and exactly how much they're impacting our bottom line of our business and exactly how stable they are. So now our business planning is, how do we match our investments and our resources to our biggest needs. And really that's just the plan, do, check, act cycle, right? I have a business plan, I execute, I'm collecting and analyzing data, so I'm doing my checking, and then I'm able to act, but I'm able to act based on data. A lot of things that we want to track or we may want to get out of an information system. This is one of the biggest needs that we're seeing out there right now. A lot of people have ERPs. A lot of people can purchase. A lot of people can do finance, which is that end loop that I showed in the first slide. But we're not necessarily seeing the inputs or the cause and effect of our financial performance. So we need to consider, and this is a lesson learned from us, right, is that we need to have an information system that matches the type of business that we're operating. And this is actually a slide from early on, and as we're able to get in businesses, again, lessons learned. High volume, low mix, low volume, high mix is kind of how we start out looking at these businesses, and we're finding that there's a lot more, and this is going to continue to generate and modify as a slide, right? We have the high volume, high mix. Things like plastic shoot and ship or stamping in a lot of cases is actually high volume, high mix because they really do perform a large number of changeover and schedule adjustments. The low mix, or the high mix, low volume, you may actually have prototyping. I've got a low volume, but virtually everything I'm doing is its own machine based on an individual design, or it's a prototype. And all of these businesses have different needs, and the performance of the business and the data needs and the metrics and measurements that should be used are different in each one. And so we've implemented what we call data stream mapping. And many people are familiar with value stream mapping from Lean. I am not a firm believer in reinventing the wheel. So what we've done here is we've just taken the value stream map as an entity, and we've implemented utilizing the systems that we're interacting with, the information that's being handled, the forms that may be used. And what we're using this for is to try to get ahead of the stream. A lot of times it takes multiple dates. I call them dates, but meetings and discussions with an information system provider to try to understand exactly what the business needs. And if we can do this ahead of time, it's better for the supplier, and it's also better for the client because they're able to show you exactly how their software will meet the needs of your business, and or where there's going to be add-ons. I don't know how many times I've seen implementations where, oh, our system will do it, but then we find out the system doesn't really do it, doesn't do it fully. That's an add-on, that's going to be an up cost. Being able to be more upfront and more aware of the business and the system being provided, we've found is good for both parties. And we implement it because we get an alignment of goals and objectives, or as I like to call it, we get consensus as to what our problems are, and therefore we get commitment on putting the resources forth to solve them. It gives us standard work so that we actually can see the cadence and the pulse of our business. It gets rid of delays in information, because what we really want is we want people to know what they need to know exactly when they need to know it, because that gives a bias for action. It allows us to do something instead of that constant loop back in the old days where it was go see what's going on and report back and then we'll pick a direction. It gives us contextualization. It allows us to know not just what our performance level is, what's our yield, what's our uptime, what's our throughput, what's our on-time delivery, but it starts to give us the reasons for each of those outputs. And that drives us to autonomous, not automated, but autonomous manufacturing, where we're able to actually understand what the what's going on, and allows our people, the appropriate person at the right place in the organization, to respond immediately to a change of state. And this can be a problem, or this can be an opportunity. We want to collect on opportunities as soon as we detect them. So if we apply our technology, and as I said before, we got to keep in mind, if you apply technology to a poor system, what you're going to end up with is high velocity waste. You're going to be able to make mistakes much faster than you ever imagined. And a couple of things to get into, right? So what do we do with the jobs that we still can't fill, right? We start out with maybe a discussion of autonomous robots or automation, being able to implement them. Everybody kind of knows what they are. Robots, cobots, two opportunities that we have. One, as a robot, requires guarding and safety features. Cobot is something that it's easy to work with. And I'm going to talk about the 800-pound gorilla in the room. This is kind of how we see automation, or how we've always looked at automation, right? People start disappearing, and then in come the robots. And that's not really what we're talking about anymore. What we're talking about is a world where we actually can't find people to do certain functions or jobs within our facility. That being the case, we got to start with what we call the 4Ds. We got to start looking for things that are dull, dirty, dangerous. And the last one that we talk about, right? The first three are pretty self-explanatory, but is that demanding job? Is it something that is repetitive in nature, but it requires a level of repetition, or something that we can't expect a person to be perfect on every single time? Or just demanding in ergonomics? Is it hard to do? Is it physical? Is it boring? Is it a lot of bending, stooping, turning? We can address those through the use of automation, and this is just kind of an image of a cobot. Allie, I'm going to go to this next slide. If you would bring up the example of the machine tending for us, please. Sorry about that, I'm muted. Okay, so the reason I wanted to bring that up though and show it is that's actually one of our cobots. When we talk about the roadshow, or not the roadshow, but the roadmap for adoption, we talked about the vision, and we found that sometimes somebody can come into a lab and they can see a robot and still not really see how it applies. So in this case, we had a customer that was using a CNC programmer to load and unload a machine. We pointed out that's an awful high-powered individual to be just putting things in and out of a machine. They wanted to understand what it would look like. So proof of concept, we actually rolled our robot out there, put something where you see a protective skin on it. That's a UR5 robot, and we're actually using it to show them how we can, use additive manufacturing and design down here as far as staging and part presentation. And we're helping them to design end-of-arm tooling so that hopefully they actually see. Now, the nice thing about this is the ROI on even the trial pays for itself in being able to run multiple machines with that programming operator. Another one that we like to think about is system integration, right? Looking at IIoT. We just kind of talked about that. How are we going to get our information? We want to make sure that that information comes in and that we're delivering it back again to the workstation, and or automating some things instead of having something, how do we normally do business? Okay, well, every time something goes wrong, I'm going to tell somebody to check something. watch for leaks, check this pressure, make sure that we're running this, make sure it's at the right level, and we task saturate the operator and or maintenance. So these days we can use sensors, andons, indicators, and let's bring information to our people so that they can make the right decisions. Augmented reality, or is what we call assistive reality, is also something that we're using very heavily here at the center. And with our clients, being able to give standard work. When we do have new employees, we want them to be successful. So we want to give them some sort of a system of instruction, a system of training, and a support system. And on the next slide, again, Ellie, if you could bring up the light guide presentation. So just to touch on what you're seeing here is not only providing standard work or an instruction to an individual operator. In addition, that system is telling you which tool to use, what order to perform functions in, so that you actually get a standard best practice. And then as you can see, when they're using these tools, the systems are actually capable of tying in to make sure that we're performing, you know, if it's a tightening, we're actually seeing the right, we're seeing the right readout. So actually collecting our quality data. So that becomes part of lean manufacturing, or leaning out through the use of technology, is to actually be able to perform the job, perform it in the right order. We're getting all of the standard work, we're getting all of the things, and we're also getting data collection without asking an operator to fill out a bunch of check sheets or spend a bunch of manual time. Okay, and here you can see, so this is our Real Factory 4.0. This is something that we're using. This is our first light guide table. We have another one on order that's coming in that we'll be using again for proof of concept. Earlier when I showed the lab, Tulip is another company that we're working with to be able to go in. So again, proof of concept, we can come to your place and help you set up a standard work or a standard work instruction or documentation. And in many cases, we've worked with partners to get a 30-day free trial. And the last thing I want to kind of touch on as we wind up is we also need to look at investing in our companies and in our employees, because again, we're talking about having a problem finding talent, but we're also talking about human and machine coevolution, the rise of digital disruptors. So kind of a perfect storm, because we're going to need people who have the ability to work on technological tools and situations. And we're going to have to upskill our people, because we know we can't find them everywhere. And these are just kind of a list, right? We have to think about the skill sets that we're going to need through implementation as we're putting it. And in implementation, we may be able to buy those. But when we start talking about support, we're either going to have to hire that, or we're going to have to train that, and we're going to have to make that part of our strategy. And one of the things that you notice is in both of these, everything that we do, folks, whether it's lean, whether it's Six Sigma, whether it's quality system, whether it's an implementation of new tools or new technologies, everything has to do with change and change management. So one of the things that we're doing, well, a couple of steps. The first one is we have 4 4-hour classes that exist to be able to talk about how to use these various technologies within systems to be able to drive business, and to kind of be able to get business owners to understand, business owners and people in business to understand what the needs are going to be technologically. We're also working with some local community colleges to see what the next step is for certifications. It doesn't necessarily have to be an associate's degree or any other kind of degree, but we have to start moving towards certification of our people to be able to handle technology. So that's kind of it in a nutshell. This is my obligatory question slide. And if you desire to contact, there's my email down at the bottom.
Thanks, Chuck. Thanks, Chuck. It's really interesting to hear about all the great work that you guys are doing with small to mid-sized manufacturers in your state. So go ahead and use that question panel if you want to ask Chuck any questions. We've got a little bit of time before the next presentation. Chuck, so how do you measure the effectiveness of the programs that you install with your customers? How can companies tell if they're getting an ROI?
So often that comes as kind of the first step. That's actually a large part of what we go in and we look at the assessment. We actually do a financial, or we start looking for some of the financial and the performance information and data, and trying to tie that right again to, as I showed earlier, how do we tie that to the overall cost of the business so that we can measure the impact and the baseline and originally, and then be able to calculate the savings from that change of state from the implementation. Sometimes when we go in, quite honestly, in the assessment, if we're still at that stage where we made money, lost money, and we don't know why, that in and of itself can be an answer. And that's usually the first thing that we have to start with as we help a company go forward is how do we establish that measurement system?
Sure, makes sense. I was interested to see that cobot video. I'm certainly hearing more and more interest in cobots in our segment of industry. As you said, companies can't find people to stand in front of their machines. What are some of the hurdles? I don't like to use that word, but what are the challenges in implementing cobots? I know they should be simpler than robots, right, with the safety systems that you talked about that are not quite as stringent. What are kind of the challenges that you see in implementing a cobot to do machine tending specifically?
So the biggest thing with a cobot that we're finding, as far as the decision between a cobot or an industrial robot, is payload and cycle time. Cobots will struggle with, I remember being in automotive and running robots at a high rate of speed, repetitively day in, day out for years. A cobot will not necessarily do that. So the amount of payload or weight that the cobot can handle and how fast you really need it to go. And you could see the cobot that we had there, we actually have that protective wrap around it. With a cobot, you have to think heavily about the environment and make sure that it's protected. So if you've got oils and coolants or chemicals or things like that, you really want to be kind of careful about. In the case of this one, we actually have to look at the end of arm tooling as disposable because we know that we're going to do damage to it over time.
That's interesting. Okay. And you're seeing more, I think you alluded to additive manufacturing with that end of arm tooling. Are you seeing that? I guess how much are you seeing that used, and where do you see the future for additive in terms of end of arm tooling?
It's a funny question because we actually started doing that here for a display. We have an automation station or system that we use in our road shows and here in our classrooms. We actually started using our additive manufacturing to prototype end of arm tooling ourselves, just to be able to. Now it may not be the end. So for this particular robot, they've already looked at it. They like the pay. They want to move forward with their own robots, and they want to invest in this. And it's interesting because we've now been able to use what we learned as a supplier to prototype the end of arm tooling that they're using, and then we're also going back and working with some other automation and companies that specialize in end of arm tooling. But the nice thing is it's growing, not just for end of arm tooling, but replacement parts, being able to very quickly model something and make sure that fit, form, function is there, allows you to go forward so that it's not trial and error. And we're finding that the development of replacement parts or end of arm tooling, we're actually able to drive that from what was once a 3-month average down to about 6 weeks.
What material are you printing, and what process are you using?
So we don't yet have a metal printer, but if my boss's boss is listening, this is my belief, my partner Michael McGray, that we need a metal printer. But we currently use a lot of nylon sintering, but we start out with the FDM a lot, just the extrusion, so that we can actually get the size, the form. So again, that's our fit, form, function. And then for a longer trial, we'll usually move from the FDMs and the plastic, we'll get over to the sintered nylons, and that kind of gives us something that lasts a little bit longer. Sometimes that's sufficient, as is the case in what we're running right now, but then long-term for something that's going in and out of a CNC machine, you really want to do it in some form of metal, and at that point, we kind of turn it over to somebody else.
Okay. I don't hear a lot about companies in our industry working with their MEPs. I'm not exactly sure. Maybe I'm wrong about that. But how do companies get involved with their MEP? Is there a type of project they should have defined before they reach out, or what's the best way for folks on this webinar today to interact with their MEP?
That's good questions. Yeah, so obviously here in Michigan, I mean, we'll share the presentation, and you can get in touch with us through the center.org. But again, there's an MEP everywhere, and I will say, here in Michigan, the MEDC, Michigan Manufacturing Association, a lot of the manufacturing associations. So if you have a local manufacturing association, by all means, if you work through them, they should be aware of your local MEP and how they can help you and support you. And all else fails, if you're really looking for somebody to help you, you can always contact us and we'll pass it along.
Excellent. Good. All right. Any more questions for Chuck before we let him go? Okay. Well, Chuck, thank you so much for a really interesting presentation. Yeah, this is all coming pretty quickly at everybody, so it's great to hear how it's actually being implemented out there in the world. So thanks again for your time today and for the presentation.
Thank you. Appreciate it.
All righty. So our next presentation, and it is the last one of our series this week, is from Hanook Kim. Hello, Hanook. Hanook is the director of the EWI Forming Center. He's also the principal engineer in the forming group at EWI. He is a frequent speaker for PMA and is a thought leader in our sheet metal forming industry. His areas of expertise are broad, and they include cold and warm, as well as hot forming of sheet metal, as well as forming technology, tribology, simulation, and formability testing and analysis. This morning, Hanook is going to share with us his vision for Industry 4.0 in the metal forming industry. He's going to discuss, in particular, how various types of sensors can be used to monitor 4 key variables that impact part quality. Those variables are material properties, die friction response, elastic deflection of the tool, and press dynamic characteristics. So please welcome Hanook.
Thank you. Nice introduction. So, Brad, can you see the screen? My screen is a presentation mode.
Yep, looks good.
Okay, good. Hi, everybody. I'd like to share some information that my center has been working on this topic over 4 or 5 years, the past 4 or 5 years with the industry partners. Before we get into that, get into the technical information, I'd like to give you some brief introduction about who we are, EWIs, and then what we are doing for industries as well as U.S. governments. So EWIs is actually stands for Edison Welding Institute. We established in 1985. We've been in our business about over 36 years. We have advanced engineering service providers, address the business challenges by implementing and implementing the engineering solutions. We have over $25 million annual revenues, and then our technical staff is 150 plus minus 10. Mostly have advanced degrees and multi-years industry experience. We have over $40 million equipments, capital equipments. Our institute actually started in Columbus, Ohio, which is a headquarters in Columbus, Ohio. And we also have our facility started in the Buffalo in New York state of New York in I think it's 5 years ago. That is focusing on additive manufacturing and automation. And what we are doing, and then for government as well as the industry, this is a kind of a diagram that we call it our technical roles. Our technology readiness level for any given technologies, a lot of basics research and some of the proof of concept has been conducted, has been studied, has been taken care of by government research lab or university side. While the private sector of the industry, they produce a part which is a TRL, technology readiness level, between 7 to 9, which is prototyping and actually the full production run. And there's a technology gap between that fundamental research as well as actual industry application, which is our EWI sweet spot is applied research, R&D, research and developments on manufacturing technologies. So here's what we're doing in the innovation, maturation, and commercialization and insertion of the technologies, which is developing process system testing and up to the process validation and demonstration with the prototype. That's just what we are doing for industries. We're serving pretty large, pretty wide range of the industries sectors. We have over I think 150 member company around the world, but we covering both aerospace, automotive, electronics, defense, and heavy manufacturing. And you can name it. We actually pretty diversified the customers basis in our business. In our technical capability, EWI, which is starting with purely the material joining and welding process. We have a laser welding, arc welding, friction stir welding, and other other solid state welding. We have all kind of welding process, and teams are actually involved in our team, in our technical expertise. And we also have a forming area that we started 2012, and then I started actually that when I get into EWIs a couple of years later. And then we have also a lot of activities on the additive manufacturing. We have a structured integrated testing group, ND testing group, and other advanced automation groups that particularly in the state of New York in our Buffalo facility. Okay, get into that forming area that EWIs, we didn't have any single equipment when I joined EWI 14 years ago, but over the 14 years, I think we established quite a bit technical capability. We have 6 different press, which is anywhere as press capacity from 12-ton small press up to the 300-ton IDA servo press. We have a capability mainly helping our customer to characterize and predict the formability and fractures of the materials, high strength material, aluminum alloys, evaluate the lubricants and tool wears, tool coatings, and also forming process design and process material selection using finite element method. And also we have been actively working on applying this AI, artificial intelligence, and machine learning on the metal stamping to improve the quality as well as increase the throughput. We have a lot of advanced tools and equipments available that is covering the strain measurements and modeling simulation tools, and also we have dedicated warm forming test cell as well as servo forming test cell in our lab. Get into the vision for Industry 4.0 in sheet metal forming. So this is actually the started from my introductions in my introduction for my talk today. The vision of that Industry 4.0 in sheet metal forming is autonomous forming process with a maximum process efficiency, is a throughput increase as well as a minimum scrap rate. This is very similar to full self-driving vision of the electric vehicle today. The people are adopting this sensor technologies and then machine learning capability, algorithm, and automation is very similar to how the automotive industries, particularly the electric vehicle OEM, started their business and then developed their platform in different generation in the FSD vision. This technologies is not intended to eliminating the people's workers in the plant, which is make the peoples are more efficient and then increase their efficiency as well as productivities for entire plant. Because that's how this FSD, full self-driving, it really help the drivers or passenger can be, they can be less on the car, especially when they have a lot of cars in traffic. They can have better control of their vehicles for the safeties for both of the passengers as well as the drivers as well. Adapting by many different sensor technologies and algorithm that based on the sensor that vision sensor are capture the images and distance that they can give a commands to the vehicles control units so the vehicle can adapt their speed and the motion of the vehicle to navigate to the final destination. Applying this technology in a similar situation in forming metal stamping, particularly the current stamping process, incoming materials are feeding to the press line, which is after blanking line. They pass through that press line. Sometimes the coils directly feed into the press if there are progress die forming process. After stamping, their visual inspection will be made. Is various different form of the visual inspection will be made by the inspectors. The good part will go to next post processing. If the good part is not okay, then it's scrap or discarded. Now, this is a pretty conventional and legacy forming process that has been people using over a decade. And then future technologies, actually some of the early adopters today, the OEM and tier 1 supplier today, they actually adopting this advanced smart forming concept, which means they are adopting more sensor. They starting getting using sensor for quality control. Okay, I want to have an idea that how much coil material properties are vary, thickness vary. So people are using the sensor to obtain that quality control, to getting the data and then quality control. That is probably first step of the getting to this Industry 4.0. Now, next step will be when I have all this data and sensor data, what am I supposed to do? If somebody develop some of the what we call the algorithm, which is really have a decision making the control box, which is based on the sensor data and also simulation data, we can actually determine that how the production process control has been changed or adjusted based on the variable that we experience in the production line. This is actually the next step of that smart forming process. People are getting a lot of data, but people don't know how to do with all the data. So there's a data analytics. The model has to be developed using this data and then producing more useful information. Now that information we actually output for the press setting changes for this case particularly. I have a couple of examples that in my presentation today, which is the press setting has been changes based on incoming material property changes, also the lubrication changes in the die. Then based on the results that instead of the humans or operators can manually inspect the part and necking and cracking, actually there's a sensor can already available today. Is a camera sensor can actually measure that and actual part geometry as well as a crack and minor necking, so they can actually report it out the process so that data can feed back to the process to the control algorithm. In this case is the forming intelligence algorithm. That is, this is a closed loop control can be actually obtained. Okay, so you can see there's a mature flow and data flow in the red line, and the mature flow is a dark navy colors arrow. I have a if you are interested in learning a little bit more about what is the state of the art, what is the state of the art in Industry 4.0, in particular in metal stamping, I really encourage you to look at the article that I recently published in early this year's. I think I published this article with the World Auto Steel Partnership. They actually published out the Advanced High Sensitivity Guideline. This is an online article. You can actually go and just download it. Actually, you can look at the article directly. This is a topic that I actually included in my article. This is a pretty extensive information that you can have a run in what kind of sensors that already being used in the industries, as well as being reviewed and by feasibility of the sensors and automation system. There's a couple of cases has been a case study I reported out in this article. I really encourage you to look at that information, not only this cold stamping but also hot stamping application as well on this online article. Also, we have virtual lab tours in our forming test cells. So you can see this snapshot, but you can go to YouTube. There's 5 minutes, I think 5-7 minute YouTube video our marketing team is created to help the people their understanding of a smart forming process and how we can develop the process control parameters using our smart forming test cell at EWI. So Industry 4.0, I think the previous speaker already covered the Industry 4.0 quite a bit. So you've been heard them many times already over three days, including today. I'm going to shorten it, but Industry 4.0 is actually a framework of that is a collection of the disruptive technologies. Basically, is the current trend of the automation and data exchange in manufacturing technologies. Now, Internet of Things is computer things also included in there. Smart factories that's defined as a fully integrated collaborative manufacturing system to respond in real time to meet the changing demands. Changing demands mean that like material property changes, incoming material property change, or thickness changes, or variation of the lubrication in the die. Those are changing demands and condition in the factory is very difficult to address and countermeasure. So the Industry 4.0 is actually the smart factory actually was actually aimed to help those kind of situation and resolve that situation without the stop the press of and then tear down and then applying the changing the cold material, which is very difficult to do in production line. These smart factories is supposed to be help that operators to they can adjust the press settings and parameters. They can work around the situation that they are facing in those situation of changing demand and condition. However, it's easier said than done because there's 3 key factors has been involved. This is I lately highlight this one: it's connectivity and intelligentization and intelligence, and also automation. This is really characterized this new industry revolution. Now, starting the connectivity, this means that physical space, internet-assisted cyberspace should be connected through the to produce data. And automation is not just integrate the automatic linear transfer system and automatic part transferring and the sensors. It's actually the communication between the sensors and then control algorithm, control panels. So that is the connectivity, and then that is help us to automate the manufacturing process and automate the services. Intelligentization is the analysis and utilization part. This part is actually as not really defined well so far. I mean, this is a really new area. People is already doing a lot of connectivities and automation side in the Industry 4.0, but this intelligence side is kind of undefined, unidentified. There's still people are developing solution that what is the intelligence it really means and how they can get this. Tools are available for industries. This is a diagram that what is a big deal, basically business value for ramp up from the transforming low data to meaningful and useful information. Because the business intelligence is set up theories and methodologies and architectures that is transform the low data into meaningful and useful data for business process. For instance, I have a bunch of sensor in our production line. That sensor will produce gigabyte of data every single day. Now, with all the data that what the peoples cannot really much, it's not limited to use that humongous data set, because that the intelligence that peoples can implement it, those data analysis is limited. That's why the computers coming in, the data science, the data analytics coming in, they actually have interpret the data, low data, and produce more useful information for business purposes. That is a very core part. And this is diagram actually is showing that basically inside and from low to high to business volume to low to high means that that's sensors and then a DEX data acquisition system can report it out the data, which is a very basic stuff. Basic stuff people has been end up this one, the getting all the data and the report. Most value is coming out from prediction side, which is a predictive analytics, which is we are talking about, that are useful data and information that people can make a decision in their production line, that especially the machine controls and press controls, things like that. And everybody, this is kind of a analogy I commonly use for how this apply this my stamping production line. And everybody using the GPS system on their phone. And when we commuting the daily work, you're commuting to your workplace every day, your GPS can help you tell what's going on. The load is road construction, some traffic, some car accidents going on. Without the GPS, your commuting time is going to be doubles or triple, and you don't have any option to detouring anything like that. So this is intelligence that we are talking about, really help you to work around that, for unexpected, changing demands and condition on the road. How am I going to adjust my schedules or to navigate my road on the road to get into that my workplace so I can still obtained pre-predictable days without having significant lost my time in the road. In metal forming process, metal stamping process in particular, we know that those are 4 key parameter variables influencing stamping quality, which is materials, income materials, which is involved with the material thickness, and then the mill specs from tensile strength, yield strength, things like that. We also know that lubrications are pretty significant roles in the metal stamping quality. And also tooling, which is also critical, that tool surface condition also change the friction condition, as well as the tool wear, as well as the tooling deflections, and then pressure distribution. Those are influence of part quality, particularly spring back. And forming process, which is how fast you run the press, of mechanical press, and also type of press you're using. Those all influence part quality. This all we know that intuitively. The point is that how our institution get into the realistic the data and then our production line. So the empirical based approaches, which is a legacy forming process, when people are getting to the split or wrinkling, they are just like cushions, or they are just the shims to avoiding this split and the wrinkle. Okay. Now the question is, if this changes happen in every different coil, because the material quality from coil, especially advanced sizing steel, that newer, higher strength material, there's more variation than conventional steel like mild steel or HSL materials. The adjustments, the press setting, only after visible quality effects can be possible. Manual adjustment can be done, which is you have to stop the press line and then adjust those shims and the condition in the press, which is increase press down time. Now, versus that, the continuous adjustment to press setting before quality defects occur, which is the prediction models can predict, like your navigations, navigate your, drivings, and help you. Navigators can help you. GPS help you to your navigation on the road to your work or final destination. You can actually have streamlined the control that your process parameters to avoiding any winkling and tearings, regardless of the incoming material properties. This is also independent of the experience of the workforce. The other big issue is that a lot of experienced tool engineers, special process engineers, production peoples, there's some aging issues of that experience, skilled workers. Those people are, after they retire, the young people, there's not enough the young workforce to take over the job in production line, which is a lot of 20, 30 years expertise actually as it will be extinct. So this is a system that actually can be leveraged with an experienced workforce, but after they retire, that knowledge and capability doesn't go away. Skills are remaining in the facility and the production line, which is a really interesting and really beneficial for that companies who can adopting this process. I'm getting into a little bit details about the people who are might be interesting with rule-based and machine learning-based control. So basically, the bottom line is that people know how they can adjust the press control to avoiding the wrinkling and tearing. That is, people already know. They can have a lot of experience to adjust the dies and the condition for the shim. But there's a situation that you don't have that control that once the production die is set it up, like springback, for instance, because springback is influenced so many different parameters. So I cannot just adjust the cushion pressures or the nitrogen cylinder pressure of the shim. I cannot adjust the springback to obtain the tolerance, to obtain the satisfied tolerance. So here that we have a multiple parameters can influence springback. So data analysts can really help us. The sensor data can give us an idea that what is that loss that the influence of springback that I can work around this various the parameter effect on the springback. This is actually what we are been working on these topics and for years. I want to show some actual application of the machine learning based process control for reducing scrap in the following slide. This is actually that actual industry experience, industry application in Europe. This is a company called, producing the kitchen sink, the stainless kitchen sinks. It's pretty deeper part, and they also produce a double sinks as well. So they people are already implementing the incoming core. They know that variation of incoming cores are incoming core properties. So they're using the eddy current sensors and laser sensor. They measure the gauge variation as a material property variation. So property means that how much the material gets a little bit stronger or a little bit less stronger. So those are really influence the part quality, springback, also the necking. And based on the information, they actually using some of the meta simulation based model. That is actually adjust the press setting. And after they stamping, they actually transfer the part in the inspection stations, which is the camera can actually measure the material drawn in, that data feed into the control algorithm. That's how they adjusting the basic press setting using this sensor data when this steep drawing stainless steel sink. Ford Motor, actually, they're also implementing this in their ODATM plan. I think this is a presentation is the 2020 PMA conference. Mr. Liskar actually presented this. They already implement the sensor in their transfer press in their ODATM plans with measuring the material properties and then material thickness and film thickness, and basically it was quality control for that, for quality control of the part. They've been working on the data analytics. The presentation is not included data analytics, but as I know that they've been working on using all the data and then develop the data analytics that probably the information will be available. But ultimately they try to, concurrent the engineering process. So usually have only one cycle that when you have all the engineering works done, characterizing materials and die design, tool design, then implement deploying into the production line, then they have basically that just any troubleshooting issues, then report it to the engineering department. In this case is actually that engineering department, or production department, they have continuously the data feeding, circling, because all the digital data from the production actually feed back to engineering data. So the engineering data can provide just their data analytics model for production control. Okay. Here at EWI's, we've been working on this topic past 4.5 years actually. We have 12 industry partners in this area. We completed like 6 different projects in our consortium, Forming Center Consortium, on this relevant to this Industry 4.0 topic in metal stamping. And in our approaches, there are 2 case studies I'm showing you in next couple of slides. First case study that how we can control or reduce the necking and cracking and wrinkling in stamping process. So first step, we are using that non-destructive sensor, which is what we call NDE sensor, non-destructive engineering sensor, which is in this NDE sensor, actually that when the material properties changes means that microstructure changes from the coil, from steel mill. Those microstructure changes can also influence the magnetic property changes. So by measuring the magnetic property with this NDE sensor, actually we can determine the mechanical properties changing. So the diagram that's showing on the right-hand side is showing that experimental data means tensile strength data versus the actual ND measurement data. So this is yield strength of the materials of the specific steel. Then you can see the correlation between the ND data, experimental data actually have a 96%. Okay, but you can see the strength of the yield strength of all, from the 230 megapascal to up to almost like 255 megapascal. There's a like 25, 30 megapascal variation from core to core. And that is actually very accurately measured, that captured with the sensor, and actually very well aligned with the actual tensile test data, which is experimental data that I plotted here together. And then using the simulation technology, simulation can give us a lot of options, because without doing the physical trials, the simulation can help us. There's a lot goes inside. For instance, what kind of press setting they have to use, how I can change the press setting based on this, the variation of the incoming material properties. So simulation can play here. So this is an example that how we can set up how we can actually determine the press motion, slide motion curve based on simulation result. And using FLD diagram, monitoring FLD diagram, we have actually pretty good correlation also between the simulation results versus the real part, scan part, with a thinning, maximum thinning is 39% predicted by simulation, with a 40% maximum thinning, so it's actually measured with this strain measurement tools on the actual panel. And then with that information, we actually developed, actually validate that press setting. So the motion on the left side, which is crank slide motion, the video, I think there's some delay of that video, but actually we can run that speed up to 12 or 16 stroke per minute. But what we define it from simulation side, we actually define some of the attached slide motion on the servo press. We can actually implement that servo press motion, and then after that, we actually that part is actually measured with the camera system. So camera, actually, we have a system that we actually measure that not only just the images, also reporting the images, but also actually measure that material drawing and cracking on the part during the stamping process. And we have all the data, then it gives us a statistical data. So how much what is the scrap blade, as well as how much variation of the blank edges, which is the flange edges, will be changed, which is influenced by lubrication as well as the material properties. Step 5 is then we loading this information into our control algorithm, which is based on machine learning, and then we actually select the die design. We have 2 different die sets. So in this case, it's that input data, sensor data, as we reported here, and then algorithm actually predict the output, which is a press setting. What kind of press setting we have to use for recommended press setting? Then in our case, our operators are programmed that recommendations in our HMI panels of the press. But if that press manufacturer down the road, if they agree to allow us to our algorithm directly communicate with the press HMI panel PSC board, this is also technically possible that our control algorithm actually directly communicate with the press control. And this is an example that we have a study for high strength material, as well as some of the bake carbon steel 340 materials. So 340 bake carbon steel is materials commonly used for the closure panels of the automotive structure, automotive vehicles. And we actually tested out the 3 different batch materials: 3MA, 340, HA, HB, HEC, which stands for material from 3 different batch of the coil. And then we found that we actually implement the 5 different press setting, and then you can see that based on the incoming material property, we actually variation of that, actually different quality results. And for instance, that crank motion, we have only one good part out of the, tried out 9. But when you get into that, when you're using the different cushion control system or different press motion control, we actually have 100% good part for this specific 340 materials by implementing this control algorithm. We actually validate both this 340 material as well as 980 Gen 3 steel, which is one of the high strength material that being used in automotive industries in this concept. Second case study, actually how we can use this machine learning to control spring back. Similarly, we measure the properties from incoming coil using 3-make ND sensors. The ND sensor actually amazingly reported out a lot of detailed data and yield strength, tensile strength, elongation, and value, anosteric value, which is if you need this kind of data in the lab, you have to contract outside, or if you have a tensile testing machine in your lab, you can actually do the testing. But any one of this testing will take 2 hours to get the testing and then getting the report. Versus what we are doing here, the ND sensor actually measure the property in less than a second. Okay, so we can have all the data in less than a second, but non-destructively, without doing any machining. The measured panels will feed into the press line. The spring back simulation also actually can be conducted in the simulation. So in the simulation side, in this case, we are using autoform. So first, sigma analysis, we do identify what is a key influence factor for spring back. So the results they're showing that lubrication are one of the key factors influence spring back and flange area, which is we like to control that spring back. So second simulation will be process optimization. So we determine what is preferred blank order force, cushion force, and the slide press slide motion using this sensitivity analysis of spring back by altering the parameters, which is lubrication as well as other cushion force. Those are key variable, and the experiment validation can be done in that in the flow chart. In our experimental validation, this is again showing that 2 different press motion, one in the crank motion in the lab, the other one is a restriking at the bottom of the center. So people using some restriking die for another set of die for calibrate to spring back or geometry for spring back issues, especially high stakes material. But this servo press is allow us to restriking the part of the press motion, so that we have a hitting in the bottom of the center 3 times, which is offsetting only 0.8 millimeter from the blanks. So they have a 3 times restriking at the bottom of the center. It does not significantly delaying the production rate, but actually more effective the spring back control. Now, one thing that I want to show you here, then we also have using camera system. We actually measure that spring back angle right on the die. We don't need to take the part and then putting in the other inspection system or patterns to capture them, to check those spring back. So we can actually get the spring back data 100% from every single part that we can stamp it in our press. The image on the right, which is a kind of snapshot of we can measure the image of that camera system, actually measure the general opening angle, as well as the twist angle, the lift up angle, which is related to the twist amount of the spring back of this our S-Rail tool. And then finally, we input those data into our control algorithm, and control algorithm has been reported out what is the input data from the sensor, and also recommend the press setting based on the data. Now, we have a handful amount data. We are not only just few data points, we have running at least like 300-400 data points in our testing, means 300-500 experimental work that to creating database. But this machine learning, one of the things that machine learning is actually more ideal for production environment, because this is to improve the accuracy of the machine learning model. You need the more data, actually more valuable, more increased, better for machine learning algorithms. So in production data, if you're getting the 400,000 part, 200,000 part in an hour, within an hour production lane, this is actually really beneficial for machine learning, getting more smarter and providing more, as that algorithm being matured, actually they can predict a more accurate press setting. For this cases, so we have running 3 different batch material, 980 Gen 3 material, 1.2 millimeter gauges, UD, UE, UF is basically representing the 3 different batch materials. We're running the 4 different press setting, press motion. You can see that restriking motion in the orange one, the yellow and orange one, that is minimize the spring back angle compared to other press setting that we are used in our experiments. Okay. So this is probably my last slide. That the main takeaway: there's machine learning AI are being adopted in metal stamping industries. I cannot disclose company name. We've been working with that particularly on this topic, but in our consortium we work with 12 different companies working on this area. But there's a lot of advances that has been made. on this area. But again, just want to keep in mind that this machine, the Industry 4.0 is not just implementing the sensors and also the getting the data and implement the automation. People already have been doing this one for a decade. This is a relate to that how we can use this low data from sensor and then produce the useful information for process control. That is a really key. That is how this data analytics and data science can play a role. We've been working on this also, supporting the industry partners through the multiple, through the multiple area. But if you are interested in that, how we can, EWI can collaborate, helping your issues in the production issues and then development issues, feel free to contact me or visit our website to find more information. Okay, with that, I can open the question.
Thank you, Hanok. Excellent presentation. A lot of really interesting work going on. It was good to see some practical applications as well. So if you have any questions for Hanok, we've got a little bit of time. Go ahead and use that Q&A panel to fire away. I mean, a lot of the case study stuff, to me, for sure, is interesting. What do you know, Hanok, about the? Do you know anything more about that sync application with the where they're using eddy current to measure the incoming, the thickness of the incoming coil? Do they have to slow their line down to allow that data? Okay.
No. Yeah, for the motors, they're already implementing the same sensor we're using in the ND sensor, and then I mean they're measuring the property on the fly without sacrificing anything on the production line. They're just running the sensor. Actually, there's a less than like a quarter-inch stand-up distance. As long as we can keep the distance from when the coils are feeding to that line, the sensor is just staying there and they keep reading the data. Okay, so this is a really great information because now OEM stamper, they can have a mature property data from head to the tail of the coil. So they can go the data to the supplier, which is really scale to the material supplier because they only provide the data based on limited number of coupon testing. Okay, but this is a really it could be really influence because of having this information. Then I mean, people have experienced that they know that the people in production they scrap back the head of tail of the coil because they know that the property is changing. Because they're part of the coil processing in the milling process. Process, right? But if they know that they can actually utilize a lot of section of the materials, they can maximize material utilization and minimizing scrapback. That is, I think, is a really useful information. But the question is that how they're going to adjust that, use that information to the process control. That is a really key. But to answer your question, there's no sacrificial things for you by implementing the sensor in the production line. They already proven by multiple industry partners.
Yeah, so that was my next question. Though, what do they do, or what can they do then at the press as that data comes in to ensure they're getting the dimensional repeatability that they need as the sheet varies?
Yeah, obviously I cannot speak about a lot of details about those things. I have participated some of the very detailed discussion with them, technical discussion. We have an NDA, but I cannot disclose a lot of detail. But what they presented in PMA conference, that's what I use in our presentation, which is public information. Based on their presentation, they are getting all the sensor data, and they are using that data to produce useful information, which is a process control. Okay. But that has not been published yet. Yeah, maybe they don't want to publish, I guess. Yeah.
Question is, are you aware of any split detection technology aside from using a vision system? A lot of parts are complicated, and is there another option for detecting split?
Answer is a yes. We actually are working on using other ND sensor, NDT sensor, and non-destructive technology sensor, called using the acoustic emission, one of them. The other one is electromagnetic acoustic transducer, EMAS sensor. Those sensors are actually capable that actually measure even necking or minor crack, especially aluminum panels. When you crack on the backside, the little necking, it's hard to capture it, okay? Because the operator has to flip the panels and check every corner of the radius area, which is sometimes it's possible, sometimes it's not, depending on how the operators are there. But the point is that yes, the answer is that those sensors is implementable. Actually, that technically possible, but we've been working with the other industry partner, actually embedding those sensors in the tooling that actually measure that part quality in the die. It's an in-die sensing, like in situ sensing technologies that we've been working on it. But what I can answer you, except the camera, yes, there's a NDT sensor that can capture those necking and cracking.
Good. Any more questions for you? So the value proposition, you're at the leading edge of this technology, you're seeing it applied, Ford talks about it, some of the big appliance manufacturers are talking about it. How do you see this? What's the timeline, in your opinion, for moving this technology more into the, the mainstream or into the tier suppliers, from your perspective?
Yeah, so that's a really good question. Because from my perspective, basically depending on the situation, but the value proposition for this technology is for using these sensors and automation and data intelligence. This is a more can be more justified for value proposition for high production volume part. Large production volume. If you are doing just stamping, like if you are running like small and medium-sized stamping company, this technology is probably too expensive at this moment, because there's some of the investments on sensors and then some the algorithm developments for your own products, which is going to be invest quite a bit. But if you're like OEM or tier 1 supplier who had a lot of stamping part daily, they have 1,000 cores they process annually in their plants, then this is a really big impact on their cost saving, and also can justify it for their investments on the sensors and things like that. So those are things, my comments to fully adopting this technology. But you can actually using some of those sensors, which can minimize some of your expenses by utilizing your manual operations, like an inspection system, which can be possible. Sensors we are talking about is anything like, steels are expensive in anywhere. It's like, could be $100,000, and then using the sensor as well as the integration system. We are not selling sensor EWI, but we have a lot of experience using different sensors available in US as well as Europe and worldwide. And we can make some recommendation that you can actually contact those sensors companies that acquire those sensors. But we actually demonstrate that all the case study that what kind of sensor being utilized. That's just my articles about it for all those partnerships. You can look at that all kind of different sensor, but there's a one that commercially available. Some of the sensor is not being commercially fully available, still in development stages. Okay, but we can help the customer to helping their selection of sensor technologies, particularly monitoring system.
Good. Okay, thank you. All right, any more questions before we let him go? All right, well, thank you very much for that presentation. A lot of good work going on there.
Thank you
for being with us today. All right, so that concludes what is our 5th annual Industry 4.0 and IoT conference for metal forming and fabricating. I want to thank everybody for attending, and thank our speakers again, and our sponsors, Komatsu and Munis, and of course our attendees for spending time with us the last few days. We hope everyone found it valuable. Again, the archive of the program, all of the presentations, will be available Monday or Tuesday, I would say, next week. You'll get an email from us when everything's ready, and with instructions on how to access the presentation. All right, so thank you again for joining us. You can go ahead and close your browsers, and I wish everybody a good day.